Oh, hi. You caught me doing what I do every day, all day, looking at really interesting rocks. And that's what we're actually going to do. We're going to actually turn to the rocks and the rock record or the geologic record to look at our next topic, which is climate change through time. So we've had a really good look at the modern climate system, atmospheric circulation, and atmospheric composition. And what we're going to do now is look at how that's changed through time. So we're going to look at principles and approaches to the problem. We'll look at things from the 10 million year to 10 billion year time scale. We'll then narrow it down and look at it from the 10,000 to the 1 million year time scale. And then we'll look at things happening seasonally and decadally. We'll look at the concept of abrupt climate change. So our learning objective throughout this topic and topic 10 as well is to understand how climate has changed in the past and what drives those changes. All right, so we're going to start off with our principles and approaches to the problem with our classic question, why bother? Why should we bother studying ancient climate? You know, you could state this another way and ask, who really cares what happened a really long time ago in terms of our climate system? We're going to go back thousands, tens of thousands to when there are just very few people around to impact climate. We're going to go back tens of millions of years to billions of years even to look at how climate has changed through time. Who really cares what happened hundreds of millions of years ago when there are no people around? Does it matter? Well, yeah, actually it does. So we should really worry about this issue and try to understand Earth's past climate for a number of reasons. Number one, past variability can show that there were extremes in Earth's climate, even greater than today, in terms of how fast climates change, perhaps in terms of the magnitude of the changes, than any we may have experienced in our human recorded history. We also can ask the question, what was the planet like? What was the Earth's atmosphere like? What was the climate system like well before any humans were here to perturb the system? Because that may be the best way to truly get what the baseline non-human component of climate change is. There's perhaps a lot of skepticism about the climate change we're seeing now, that it may be just part of a series of natural cycles. If we don't understand what the pre-human baseline was, we can't answer that question as well as we possibly can. We might also ask the question, how periodic is climate change? You know, we're in a warming cycle now. Is the warming just part of a cyclic period and eventually things will turn around and go back down and then we'll be okay? Or are we on part of a trend that's unprecedented and not cyclic and not going to sort of self-correct? So by understanding ancient climate, we can gain insight into all of these questions. So we've probably answered the why bother question well enough to say, yeah, let's go ahead and consider this topic. So we have to consider factors that have been influencing climate on various timescales. So we've got greenhouse gases. We're aware of that from our study of the modern climate system, how important greenhouse gases like carbon dioxide and methane and water vapor are. And so one question is have these greenhouse gas concentrations in our atmosphere changed over time? We saw a few topics ago, plate tectonics, that was an important driver of moving volatiles, including greenhouse gases, from the Earth's interior to its exterior through plate tectonic activity. When plate tectonics is more active, there is more of these gases being put into the atmosphere. So there may be changes just from the actions of plate tectonic in terms of the levels of greenhouse gases in our atmosphere as a function of time. Solar energy may change through time, the output of the sun and the incoming solar radiation. Changes in the Earth's orbit. As the Earth goes around the sun, its orbit is just not stationary and static through time, but as we'll see, it actually changes. This may have an influence on climate as well. And one last interaction we'll look at that affects climate is interactions between the oceans and the atmosphere and feedback mechanisms between the two that affect changes in our climate system. All right, well, who reconstructs geologic records of climate change? Anybody? Who would reconstruct a geologic record of climate change? Well, perhaps geologists do. We'll now go through some examples of these proxies, these geologic records of climate change. We'll turn to an organic deposit, tree rings. Here's an example of a tree, and this particular oak tree is from Arizona. And the way tree ring works, I'm sure you guys are all familiar. Oldest rings in the center, youngest rings at the margin. And we can actually go through time. And the dendrochronologists, experts, and these are particular ones have been studied by dendrochronologist Dr. David Staley, University of Arkansas, as well as Dr. Malcolm Cleveland, the same university. Dendrochronologists can actually count microscopically every one of these seasonal layers in these tree rings. This particular one goes all the way back to 1834. So we know that's when the tree was first beginning. Kind of blows you away, doesn't it, that somewhere right around here is the tree at the time, the outer layer of the tree at the time of the Civil War. Somewhere not too long after that is when I was born. And when you guys were born is somewhere right around here. So we can tell time quite precisely and accurately with tree rings. The other thing that tree rings are really useful for is you can see that some of the rings are thicker, some of the rings are thinner. All other conditions being equal, this usually gives us a clue as to water availability, basically rainfall and temperature. More it rains, with all other factors being equal, the thicker a ring the tree will lay down. So these have been used to reconstruct paleo drought histories. This is an important climate proxy for telling us about past droughts. To test whether you understand this or not, to test your knowledge, look at the next image, and you can see a microscopic slide of the tree rings. And on this microscopic slide, my hand's going to wave across, and we're going to go from the oldest part of the record to the youngest part of the record, and you tell me when to stop when we get to this youngest part of this record. Yeah, right there. If you stop me right here, you are correct. You've well tested your knowledge. This thicker layer is indicating when things were wetter. These thinner layers are indicating drier times in the past. That's how tree rings work. Next, we're going to talk about speleothems. So speleon is from the Greek root of that word. Speleon in Greek means cave. And speleology is the study and exploration of caves. Because ology means the study of. Speleothems, same Greek root, speleon meaning cave, them means them things. Speleothems are them things that grow in caves. Full disclosure, I don't know what them means in Greek. But speleothems are certainly the formations that grow in caves. The key thing on all of this is that we have radiometric isotope methods for accurately dating the growth layers, individual growth layers in these cave deposits or speleothems. And then we can measure various chemical elements or other isotopes that occur layer by layer over a long time series. Could be thousands of years, could be hundreds, could be decades. Speleothems grow over a wide range. We can measure various chemical elements and isotopes that may give us clues as to the composition of the water and how that changed through time. So this is really nothing more than a frozen-in mineral deposit that records changes over time of the composition of the water dripping into the cave. Also, it may record changes in the amount of water dripping in the cave. Much like tree rings, when things are dripping, raining more, dripping into the cave more, these things may be growing faster. It's international sign language for a speleothem growing faster, as opposed to during drier times, they might be growing a little bit more slowly. So we can piece all of this together, the amount of water dripping into the cave and its composition, to reconstruct what was happening in the atmosphere outside of the cave. And that's how we use speleothems to reconstruct ancient climate. That's how speleothems are proxies for ancient climate. Some speleothems, if they're growing really fast, or if they're growing for a really long time relative to others, can become quite large. In this case, the sample, which we call the big boy, is approximately 2 meters in length. Analyses are underway to determine just how long a period of time it's been growing over. Be happy to hear your guesses as to what the total amount of time captured in this layered mineral deposit is. Well, one of the last climate proxies I'd like to chat about are ice cores. So you can see from the image, much like all the other deposits we've been looking at, if you have layering, oldest layers of in a glacier on the bottom, youngest layers in the glacier on top, we again have a great way of telling time. A lot of the glaciers lay down seasonal banding in the ice, and then the ice might be able to tell us something about perhaps the atmospheric composition. In fact, the diagram we've looked at most frequently this semester has been this history of atmospheric carbon dioxide, the Antarctic ice core up through the Mauna Loa. Those are modern atmospheric samples of air, reconstructing CO2 on the y-axis versus time. So this is perhaps the most iconic figure in climate change science. It really set a lot of people thinking about climate change and put ourselves in context in terms of the history of our planet. And we've talked about this a number of times in terms of the scientific method, the rigor of reproducibility, that no one on either side of the climate change debate actually questions these data. Let's talk a little bit about how the data are collected and about their reproducibility. So you core through the ice as shown in the upper right image. Drill a core down through the ice, pull up these cores, count those layers back through time, have some independent means of conferring those hand-counted dates. We have a time series, and then how about the CO2? It's easy to understand time when you have these layered deposits, how we can determine that, but how do you determine atmospheric CO2 from this? So it turns out as snow falls on a glacier, as the ice is forming, it's trapping little pockets of atmospheric air. And if you look at this curve here, the blue curve and the red curve, this figure we've looked at a lot of times this semester, one thing to look at is that there are little blue dots hiding behind the red dots. So where the Antarctic ice core record comes to more modern times, where it overlaps with the direct atmospheric air measurements, the Mauna Loa are the red dots, right? Blue is ice, red is the modern samples of air. You could see that they're right on top of each other. The blue are really hard to see because they're directly overlain by the red. Think about the reproducibility of that and the rigorous approach of the scientific method here in evaluating reproducibility. You go down to the bottom of the planet, you core down through the ice, you count back decades, you measure the CO2 through this air pocket extraction mass spectrometer fancy method, and then you go to the top of a mountain on an island in the middle of this ocean, nowhere near the bottom of the planet, this is more in the middle of the planet, on the top of a mountain, capture atmospheric air there, make those measurements over time, and you get them exactly reproducing. I mean, these things, these methods of measurement, these locations couldn't be more different, yet they're right on top of each other, showing the rigorous scientific method being applied here, and why no one on either side of the climate change debate, if there is one, doubts the validity, accuracy, and precision of these data. So those are the various ways we can reconstruct past climate change. I've showed you samples of all of these proxies, from sedimentary rocks to corals to tree rings to speleothems, mite and tite. Now let me show you a sample of the ice core from Greenland polar region. Got it right here to show you. Oh man, I forgot the cooler. Damn, the National Science Foundation will never fund me again. Don't be alarmed, I was just kidding about that. Okay, so we've gotten over that, and now we can move onward. So the first thing we're going to do is go back in time to reconstruct past climate and show some examples of that. So before we go back in time, we have to have our time scale down. So the next image you're going to see is the geologic time scale. And this diagram, while complicated at first, actually becomes pretty simple once you look through it. We're going to start here with the about 4.6 billion years ago when the Earth was formed, and we're just going to go rifling through time there. The entire geologic time scale is on this left-hand diagram, right? It starts at 4,600 million years, which is the same thing as 4.6 billion years, and it's 0 at the top. That's us right at the top. Okay, now we can see those top sort of 600 million years right up there, take that and widen that up, and that's what's shown on the right-hand column, going from 600 million years ago again to today, 0 at the top. Now we've gone through a lot of geologic time just here. We're going to focus on these younger rocks, is really the best known part of the geologic record. They tend to be more well preserved, they haven't been metamorphosed as much, they haven't been consumed by plate tectonics as much. All right, so we're going to go through that, but just one note where we came back to older rocks earlier this semester. Do you remember we came right around here 1,100 million years ago, or 1.1 billion years? Do you remember what that was? That was the age of the granite batholith, the igneous intrusion that made enchanted rock here in central Texas. Okay, we're going to jump forward and go through this time period, the last 550 million years or so. This eon is referred to as the Phanerozoic eon. The eras that can be broken out are the Paleozoic era, the Mesozoic or Middle era, and the Cenozoic, the most recent of those three eras of the Phanerozoic. And then we can break them down even to geologic periods: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Tertiary. And at the very top here, the last couple of million years, is the Pleistocene time period. We're going to focus on a couple of these back through here. We're going to look at the Cretaceous time period, about 100 million years ago, and we're going to look at the Pleistocene time period. And then we'll get even younger than the Pleistocene. The last 10,000 years, really hard to see here, is called the Holocene period, Holocene. Also blows your mind and humbles you somewhat when here we are living on this planet, being stewards of this planet, yet is it really our planet? How long have we been here? So if you take the amount of time that we've been here and compare it to the age of the Earth, if we look at the UT Tower, you consider the height of the UT Tower as all of geologic time, then the amount of time that we people have been here is equivalent to the thickness of this sheet of paper. So someday if you have a chance to get a tour of the top of the tower, bring that sheet of paper up there and compare that with the vastness of geologic time represented by the height of the tower. Okay, so let's consider how climate has changed through geologic time. The next figure we're looking at is a diagram that shows glaciation as a function of latitude on the y-axis and time on the x-axis for that Phanerozoic period, right? The last approximately 600 million years. All right, so when we have glaciers coming down to low latitudes, that means it's cold, right? When we have no glaciers at any latitude, like here, that means it's warm, right? This period of time back here, around 300 million years before present, glaciers coming all the way down to 40, 35 degrees latitude. That's a very cool time. Last 40 million years or so, very similar situation. We call these times of extensive glaciation, we call those time periods ice houses. The Earth was relatively cool. The times in between, we call those greenhouses. Shown in this warmer color are the greenhouses, and the cooler, bluer colors are the ice houses. So along this time scale here, you can see blue, pink, blue, pink, blue. So there's some flip-flopping back and forth between these warming periods and these cooling periods on Earth. It's not going in one direction unilaterally. It's not a runaway ice ball. It's not a runaway boiling of the oceans. There's some overall range in which Earth's climate has varied over time. And these are pretty long time scales. These greenhouse and ice house periods are tens of millions of years long. What possibly could have caused it? But first, how could we possibly have reconstructed this? What is this data based on? How can we tell where the glaciers have been? Well, one way we could tell is by looking at the marks that the glaciers leave behind. When glaciers move over rocks, they pluck up pieces of the rock and they keep moving, and they entrain the rocks at their base, so the ice sheet is moving and moving and moving, and it's got these boulders and cobbles and gravel at the bottom of it, of the rocks that they've plucked up as they've moved along with great force, and they're weighing down with great force on the new rock that they're moving over, and as they move over, they're kind of scratching them. The rocks on the bottom of the ice that it's entrained is scratching the bedrock beneath it, the surface of that bedrock beneath it, and these things are called glacial striations, or slicken lines is another fancy term. There's a couple of ways we could get those. One way is through glaciers moving over rocks. Another way is when rocks move past each other by faulting. In either case, never been around when it's happened, but you can imagine that there's probably some great sound that's been produced by the ice moving over the rock or the rocks moving past each other. It may have sounded something like or it may not have. I've never been, and I've never seen such a video on YouTube to know exactly what it sounded like. So that's a little bit of speculation on my part. In any case, these striations are left behind, and that, along with other features that are indicative of glaciers being in an environment and the environment being cool, things like the vegetation, the kinds of animals that are found, basically the fossils, these vast different records of past change, are ways that scientists reconstruct that we had these ice house and greenhouse periods in the Earth's past. So, one thing we may ask is, what might be a cause? What are the candidates? As they said in the movie Casablanca.
Round up the usual suspects.
Who are the suspects that we're looking at here in terms of being guilty for causing these changes in Earth's past climate? One thing right off the bat we might think about are greenhouse gas levels in the atmosphere. So on the next diagram, you could actually see reconstructed levels of greenhouse gases in the Earth's atmosphere. In this case, it's CO2. So it's paleocarbon dioxide levels in the Earth's atmosphere from these geologic records of climate change. And there's two curves being shown here. In red is a model that's been created, a theoretical model, and in black are those proxy measurements, right? Those are the geologic records. So you can see both the model and the proxy show that during these greenhouse periods, things are much warmer. During the icehouse period, not warmer, but they were warmer, but they're associated with levels of very high CO2. Remember, today's CO2 in parts per million is about 400 parts per million. These levels back, say, in this greenhouse period about 100 million years ago, were up around 2,000, so 5 times what we see today. Back earlier, about 500 million years ago, it looks like they were on the order of 6,000 or 7,000 parts per million. Multiple times, factors of 10 or more levels of carbon dioxide in Earth's atmosphere than we have today. This apparently can explain this shift between greenhouse and icehouse climates, shifting amounts of carbon dioxide in the Earth's atmosphere. So this is quite fascinating, is it not? Would you agree?
What? No.
I'm waiting to hear if you would agree.
No. 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 Yes.
Okay, I think we all agree that it's fascinating.
I mean, no. No.
Where does the CO2 come from that creates these greenhouse periods, these warmer periods in the past? We kind of know about what an icehouse period is like because we're in one now. We have glaciers, extensive ice caps at the poles. There were more extensive times in the past, but there are times in the past, if you look at this figure right here, when there was no ice at any latitude, no glaciers at any latitude, much warmer than we've experienced today. So what caused these greenhouse periods, the buildup of CO2 in those periods? That's a first important question. The second important question is, why are there cycles? If there's some source of CO2 that was, being contributed to the Earth's atmosphere, why didn't it just continue to go up, up, and up? Much like we're seeing CO2 over the last century, and it's projected into this century, right? It seems to be a sort of a monotonic or unidirectional increase, getting higher and higher as a function of time. That's not what happened in the past. It was high, it was low, it was high, it was low. It went through some cyclic back and forth. Why are there cycles? Does that give us some clues as to what the mechanism may be? So let's talk briefly about the mechanism that might be responsible for these cycles and carbon dioxide levels in Earth's atmosphere, and therefore what would be responsible for Earth's changing climate on these timescales of tens of millions of years that we see. So the concept goes that it's actually a function of plate tectonics. We know that plate tectonics changes its sort of rate of activity, rate of seafloor spreading. Those sorts of parameters are not exactly constant through time, but they actually change. And those changes in tectonic activity will cause, during more active times, will cause more abundant exhalation of volatiles, including things like CO2 from the Earth's interior to its exterior, namely to its atmosphere. So we're adding CO2 to the atmosphere on these long time scales of more active plate tectonic periods. Okay, but again, that should just, as plate tectonics adds and adds and adds over time, it should just keep going up, up, and up. Well, so as it turns out, that good old weathering, chemical weathering and physical weathering of rocks is actually helping to keep this CO2 from going unidirectionally higher and higher. So what happens is that chemical weathering uses carbon dioxide from the atmosphere. We can write out a bunch of reactions of taking mineral formulas and carbon dioxide and water and rain, some water from the sky with CO2, or have the water go through soil and pick up even more CO2. You make a weak carbonic acid, and that weak carbonic acid can attack minerals, and that is the essence of chemical weathering. When you look at those reactions, CO2 is on the reactant side of things, but it's not on the product side of things. So that CO2 is consumed and converted into other chemical molecules, a lot of it just washing into the ocean. And what happens is that consumes the CO2 from the atmosphere. And so the way you can consume CO2 from the atmosphere is increase the rates of weathering. After you have a period of very active plate tectonics and you're building mountains, you're exposing fresh rock to these weathering processes, the weathering rates after these periods of active plate tectonics will increase. So the more active or more rapid or more vigorous plate tectonic episodes help release CO2 from the atmosphere. It builds up, things warm and warm and warm. And then as a consequence of building new mountains and exposing new crust, you're also increasing the rate at which things are weathering. The warmer climate also aids in that as well. So with a warmer climate, more fresh rock exposed, you're weathering things more rapidly, and that's going to draw down CO2 more rapidly than previously. So it's this weathering phenomenon that acts as the policeman. The plate tectonics is driving the increases, and it's the weathering that results from that more active plate tectonics that's the policeman in keeping things in check and drawing the CO2 downward. And that's why we have cycles. So to look at two examples of what the Earth was like in the past, we're going to go back to a greenhouse period, the Cretaceous time period, and then we're going to go back to an icehouse period, the Pleistocene time period. The first one's about 100 million years ago. The second one is tens of thousands of years ago. And we're going to have a look at what the planet looks like and what may be responsible for those differences. That's what we'll do when we see you next time in class. Till then, enjoy your rocks.